So you were back in Bombay in 1960.
Yeah.
That was the year I joined, so I remember it very well that when you came. And so you continue to do work in the kind of analysis and or did you already start?
No, I had
drifting away?
already started drifting. See, the reason why analysis, of course, although I did good work, I think my real interest was in geometry, which of course kindled by the lectures of Schwartz and complex manifold. But then since he also talked about the elliptic equations for Hart theory, somehow I could get something there and went. So I thought, okay, I don't think very consciously. I said maybe I should move from there because that's not where my real interest was. So that was the reason. And what's the first work I did? Yeah, with Ramanan, I think.
Universal connections.
Universal connections. So that's already changing into differential geometry
In
from
the
there. Yeah.
year you came back, you organized a seminar
Yes.
on deformations.
Yes.
right?
Correct.
And did some people take to deformations at that point? From that
Yes, I
seminar?
think there's one person who took to deformations. We see.
No, I did not attend that seminar. I learned deformations from you later.
Later, no, what do you
Not in
mean?
the
You mean
seminar.
at that time? Okay. At that time, perhaps nobody took directly, except that it helped me to, I suppose, to learn the subject better. I mean, Ramanan also at that time was not so much took to deformations. So I ran a seminar, but there was a lot of interest. People attended, but what was the outcome for the others, I cannot say.
The next year also you ran a seminar,
I don't remember.
which I attended. So I
what
learned
was that on that? What was on that? What
it's
was
the
the
different geometry.
different geometry.
And, some connections and some Riemann geometry, that's
Yeah.
the kind of thing you did.
So I first went into this differential geometry, and then I think Ramanan and I proved a very good theorem, which is very much used by physicists and so on. Somehow, I think, at least I felt, maybe Ramanan also, that our own capacities were somewhere else, real, capacities. I mean, this is nice theorem, even today quoted and so on, but somehow, at least I was not.
Right? It's kind of, the Chern-Simons invariant has something to do with that, right?
Yeah, they used, the Chern-Simons used that theorem in their paper. And also, these people like Chern, he once told me, that's the most important paper, one of the most important papers in, differential geometry. But he never writes it anywhere. What's the point in telling me? I know that. So that was the, immediately. Then I started working with Seshadri. After the work of with Ramanan.
After Ramanan.
After Ramanan. And so, this again, as I told you, we were interested, we knew about Weil's paper thanks to Ramanathan and so on. And in the meanwhile, Kodaira-Spencer, if you see whatever theorem we prove, it is about one thing is equal to another thing. But that's not how it's proved. You must take all things with the given property and all things with the other property and then compare. That means you have to deform one and do that. That's why the deformation theory of Kodaira-Spencer comes in. So once that, since I was very familiar, we first started writing a paper on that deformations, just to give a structure of a complex manifold on representation and so on. That was the first starting point. The second paper is the more important, but this is what gives you the framework, and also that's what I talked about in 64 conference, you said, okay?
1964.
Conference. That's why the first part of my work with Seshadri is what I asked. Also, at the same time, after we worked with Seshadri, Ramanan's thesis was also a problem, which I suggested. The problem was there before. He didn't know this.
Right.
And then, because of my work with Seshadri, it gave some more insight into that. And he solved the problem very nicely.
Okay.
That was, by the way, the universal connection was not his thesis, Ramanan's thesis.
Universal connection?
Was not Ramanan's thesis, it is this homogeneous vector bundle was his thesis.
And so tell us about the 64 colloquium. You were certainly very much involved in the organization of that colloquium.
Yeah, I think that's something which people should know more about that. Because it's called, I think, differential analysis. So, by the way, everybody uses the word differential analysis today. there was no such word before the conference, and I think some conference organizers coined the word. So what's the point? The point was, usually a conference, okay, algebraic geometry, only algebraic geometries come, or functional analysis, only functional analysis come, and differential geometry and so on. Here we wanted people, really first-year people, whom I'll name soon, from doing hard analysis and topology and differential geometry, all these people to come together and talk. For example, I mean, let me give you examples of this. In hard analysis, for example, Groding was there and Hermander was there. I mean, there were others, but just to give it. Then in what will be called topology, Milner was there, Smale was there. And Atiyah Bhatt were there, and many more names, and Malgrange. Malgrange was there. At that time, he proved the so-called, what we called, differential Weierstrass preparation theorem, which was
Now it's called Malgrange preparation.
Malgrange preparation. Now it's called Malgrange preparation theorem. So he talked about this, which is really both a combination of analysis and differential thing and so on. So the idea was to bring together all these people and some algebraic geometers and so on, and to have a really to understand what's happening at a very high level in different fields. Not the same normally, of course, that's also useful. You get experts and get to know. But it was, completely different. And I have,
It was a week-long,
10 days.
usually 10 days, I
I
think.
see.
So that was, I don't know whose original idea was that. Maybe even Casey's original idea, to have such a conference, such a colloquium,
Right.
not just the more.
Right.
But
One.
the whole remarkable point is everyone came, all these big shots came to this
Right,
conference.
right.
It was, it's around the time Tata Institute was getting known. So already all these people came. Maybe I can even name some more.
Right.
But,
Then you had a number of students starting from around that time, I suppose. And
I spoke in the colloquium.
Right. Yeah.
He must have been responsible.
Right.
on defamations, in fact. On defamations, I remember. And I spoke about my first part of my work with Seshadri. Sorry, what were you asking?
No. I was talking about your students. That is the time from when.
See, I was very fortunate. Really, some brilliant students. Even though what I say may embarrass some people here, but let's forget it. Okay. So my first really student was Ramanan, and then Raghunathan, then Patodi, who unfortunately brilliant mathematician, passed away at a very young age, 31 or so. And then, I don't know in which order, Ramadas, Mitsure, and also Parsadi, who works on works on this representation theory. And so they're all, see, even all of them, even their very first work,
have been
have been immediately recognized.
Right. Yeah.
Of course, luckily, they went on to prove, because not happily went on to prove.
Right. So it has been, during your stay or tenure at TIFR, you always had somebody or the other working with you as a PhD student, or there were times,
yes,
more or less?
But I think most thing which I did in TIFR, my collaboration with Ramanan,
Right, okay.
who used to really work hard in a completely new subject. See, they work with Seshadri, Mumford, myself, threw up a whole field. But then you have to prove theorems to make it even more.
Right.
So that was my most collaboration. But also students almost all the time.
Yeah.
And in fact, I should not probably say that, I like to talk to people. Okay?
Yeah.
And in some sense for me, as they said also of Kodaira, who is my hero, that for me, ideas come when I talk to some people. It's not that they say something or something like this. Suppose you just
Being
open
able
up
to
your
talk,
thing,
yeah.
otherwise,
Yeah.
So that way I also benefited by talking to my students. And I'm sure they also benefited. So, it's a remarkable set of students. And
Has anybody ever told you that outside of TIFR, people think that you are not a person who talks?
yeah,
That's the impression
it's a
that-
very interesting thing. No, because people have told me, I am supposed to be somebody aloof.
Right. That's,
not easily approachable.
Yes, that's
And
the
then people ask, how did you have these
Right,
students?
right.
I think, as somebody else has said afterwards, I mean, just probably I'm shy, basically a shy person. But then once that shyness is broken with somebody,
Right. Then you are, in fact, that's
Yeah.
what, yeah.
that's what I think.
Right.
See, they used to say, Narasimhan will just walk without, just like that, looking, without even looking at me or something. It's not because I don't look at them. Maybe I'm thinking of something else.
Right.
And also the way I get mathematics, I think, is somebody correctly pointed out. Only I realized what it was. That I just go on walking and things are there. I pick them up from time to time.
Right. Yeah.
So that also, I mean, anyway, the main
Right.
point is
No,
I
yeah.
like to talk to people because I don't know, I have 15, 20 collaborators. This cannot happen without this.
No, of course. Yeah, of course.
But that is absolutely correct statement. I won't say withdrawn person, a shy person.
Right. Yeah.
And Chandrasekharan left within 5 years after the return from France. So during that period, how was your interaction with him?
Oh, it's excellent. I mean, I knew him very well during this period. And apart from mathematics, which we didn't touch so much after at that time, earlier I had a lot of contact with mathematics, but we used to talk quite often. And I learned from him how to administration. Because he used to be very, very meticulous in everything. Everything has to be precise, meticulous. The way he organized the conferences, colloquia. I mean, even today they follow exactly what he did and right thing to do because everything was well meticulously planned and organized. Okay, I mean that's one thing. And also how we dealt with administration at difficult times. It was not very easy, the early days.
Right.
And also sometimes by advice. For example, I remember one advice. See, when he went away for a few weeks or 1 month, I was in charge of the department first time. He said, when you're first in this kind of position, you feel you should, clear our table immediately. You should have nothing at the table at the end of the day. He said, don't do that. If you want to reply something, wait 1 day. Nothing will happen with the 1 day. Like this, there were many other things. And also I learned from him. He was at that time secretary, maybe president of IMU, International Mathematical Union, which, for example, organizes ASILOM, but I'm talking about this, ICM, and also it is in charge of giving the Fields Medal and so on. So he was very closely involved, and therefore I got to know lot about how these things function in the world and so on, this kind of mathematical establishment, as we say, how it functions. So this was very useful. For me later, I remember when I was a member of executive committee, the secretary of she was the secretary of this Spanish who was the secretary. So next time when I was actual member, she asked, you seem to know so much about this IMU, how do you know that? The first time you go, you think, you are a novice, you would know. But, these kind of things, there's no doubt. For me, he is the person who made many of us, directly or indirectly. But for him, it would not be the same. And I was fortunate enough to be also close to him during the last 4 or 5 years.
Would you agree that he has not been adequately recognized for his contribution to international cooperation, things like that in mathematics?
Forget international cooperation. For what he has done for Indian mathematics, he is recognized, I would say. No, international thing, outside, yes. I remember once, Chandrasekharan, after he went to, he will not go out. He will not travel, even within Europe. But there was then Henrik Arthan, who was then the president of IMU, wanted to have a small meeting to sort of recognized him after he has retired, after Casey has retired. And it so happened, myself and Seshadri happened to be in Paris. So there was a small, nice gathering while people spoke about this thing and so on and so forth. See, there are one or two people, disgruntled people who may say something about this thing. But I don't think it is, everybody recognizes. Also, it's at a time, which I will also talk about later if we have time, his period as the Secretary and President of IMU was very crucial because it's at that time there was this also two camps, first world, third world, and this kind of tension or even perhaps a friendly tension or whatever it is. And then somebody has to sort of negotiate this.
Right.
And he was an Indian in some sense, I mean, and also everybody knew his, and also many of the initiatives which these people take now were all started by him. So I would say, see, I don't know, the younger generation, they may not know his name. But when he was there and after a few years, he was quite recognized by important people. In fact, I remember Seshadri and also said a few words at that meeting or something like that.
In some sense, he set the pattern for Indian mathematicians taking an interest in international activities.
Exactly, exactly. Because, see, and he was also, of course, he also tried to take our help for something, you know, which is good because you get to know. I mean, okay, people will say, oh, he's taking their help, okay. But then it also benefits you, and also you know what it is. For example, suppose you have to, write a letter or something. You give a draft. That also makes you know what is happening and also where's the right thing and so on. So this is a part of your training for doing something for mathematics, not only your own mathematics. And there completely it is by just watching him or just his advice and whatever he told me. That made a big impact on me.
Would you like to say something about your connections with Baba, if any? And
There
the
was not
relation-
much. There was not much.
And the relation between Sanjay and Baba, do you know anything?
That is very complicated. I don't want to get into that. It's a very, very complicated relationship. It's
Sometimes said that he drafted the science policy resolution of the government of
that I
India.
have also heard.
So you don't know directly whether it's true or not. He never spoke
Yeah,
to you about
he
that thing.
seems to have said something. I don't want to be, but my memory is not very good. Maybe he said something. And by the way, he wrote English beautifully. And in fact, he was hesitating when he was studying in the early days, whether to take to English studies or mathematics. He was supposed to be good in both.
I see.
And that also helps, you know, the international things, everything you have to do.
Because, yeah, you
Not
have to
only
do
you have to know how to deal with these guys, but how to write. This I'll tell you. Lyons, who was the president of IMU afterwards, told me once, you see that the rules and bylaws, Lyons himself told me, were of IMU were written by Casey. Lyons said, you know, if you have any sensitive or tricky problem, you have to only look at that. There's an answer. So that means how much thought must have, gone into that.
I'm also told that the ICM statutes are also written down by him. And the same thing is being followed to this day.
That's possible, sure. So, see, there's this establishment, you know, this mathematical establishment. To break into that is very difficult.
Right.
And even now, I think Casey somehow, maybe they found him useful or whatever it is, first broke into this. And that was the first breach from which you can, you could.
Yeah, right. So
In the period, did Marshall Stone come to India? Marshall Stone and Casey were also supposed to have been close.
No.
Right?
Yes, but it was before. What I heard, this I'm not sure. How did Casey means K. Chandrasekhar, okay, for others, and KGR and Meenakshi Sundaram go to Princeton. The story I hear is, you know, Stone is a very nice man, well known and very nice. He used to like to travel. So he came to Chennai or Madras at the time, and I think he knew Racine. Racine must have told him, you know, it will be good for Meenakshi Sundaram, Casey and K.G. Ramanathan to go to some place in
Right,
US
right.
to do this. Okay. And the story is that Stone arranged it with Institute for Advanced Study. I think Binod Sundaram and he went, Casey went, and then next year Ramanathan went. This is the story I heard.
So, tell us something more after Chandrasekhar left. What was TIFR like? Well, maybe first we'll speak about your own work at some time. You kept moving from field to field.
After my first work with Seshadri, I mean, people started calling me algebraic geometer. I didn't even know I was algebraic geometer in the sense that Proof and others used many things, okay? And then, as I said, the long period of collaboration with Ramanan, which pushed that field up and up. Boreal invited me to go to Institute for Advanced Study. So I was visiting there, and then I met one Japanese mathematician called Wakamoto. And he was one day walking in the streets of Princeton, and then we got introduced to him. And then I still remember, he said, I'm working with discrete series. I proved a non-vanishing theorem, Wakamoto said. I said, probably not nicely, oh, but people prove vanishing theorems, you prove non-vanishing theorem, I said. So just for. And then we started talking to each other. I didn't have any experience with a discrete series or something, but I had some other inputs from my other studies. And we, combined this together and proved the first breakthrough in that conjecture. And it seems some of the big shots were trying that even that year. And Wakamoto told me they are very unhappy now. These upstarts come and do that or something. And that was we did the Hermitian symmetric case. Non-Hermitian symmetric case, you cannot use the usual holomorphic things. You should Dirac operators. That's what I suggested to Parsavadi as his thesis. So that's the. But I was very happy, even though very happy, because it's in a field where I had no expertise. I could make some contribution.
Right.
And then physics to some extent, that's just.
That was much later.
Much later, I
the
don't remember.
80s, right?
80s.
That's when Ramdas became your student.
But so, being in TIFR, this whole business about physics, very often mathematicians talk about the proximity and the nature of the subjects, at least the theoretical physics, how it is close to mathematics. Now, we haven't seen many people actually moving over or even collaborating. In your case, how did it actually happen?
See, it first happened because some of the work that I did with Ramanan differential geometry, the people working in so-called gauge theory were using it very much.
Right.
And then even that's not so surprising since gauge theory is related to connections. But then I found also later the work that I did with Seshadri and Ramanan is also used very much by very top level people in theoretical physics. So I start wondering, what are these guys
doing with your with your stuff? Okay.
And then slowly I try to understand what they do. And there I must say, it is a long process to understand that.
Right,
It's not something which you can. Their language is different and our way of thinking is different. But I had, of course, Divakaran.
Of course, yes.
And he is a physicist too, for others. And we were friends because we used to play bridge. And then after bridge party or something, we used to sort of talk in mathematics and physics. For the first, I think, few months, I think there was no communication. And slowly, see, what I found was, if you have patience and goodwill, and people who are prepared to talk to you without saying, oh, you don't even understand this. Either way, mathematicians studying physics or something, you can learn something. It doesn't mean you understand physics, for example, mathematicians.
Sure.
But in my own case, what happened, I think, was somehow by talking to these physicists and then reading their Divakaran and reading those papers, I made up a dictionary for myself between terms in physics and mathematics, which are related. So that if I see a statement of physicist, I could often translate it into perfectly mathematical statement. And the amazing thing was the physicists not only used our results, they came with really big insight into the problem, which mathematicians didn't think about. And with theorems also. Theorems mean statements. Of course, they never proved, but as I say, it is not their job to prove theorems, it's the job of mathematicians to prove theorems.
Prove the theorem.
So, I mean, and then later, by some of the things suggested by the physicist, so I wrote some papers with others, Ramanathan and so on. So in other words, the first one is gauge theory, second one is so-called conformal field theory. So, and also even one of my well-known papers with Dresse was sort of not motivated by physics, meaning the physicists had something.
Right.
So they defined a divisor, and then they said, oh, this gives a line bundle. It's not always true. In the particular case, one has to prove it.
Right.
And so I said, I mean, why do these people say it's a line bundle and so on? And as Bott says somewhere, yeah, it can be proved it's a line bundle, but this is the kind of thing mathematicians bother, not physicists. So, I mean, that's how it is. In some sense, I cannot claim I understand physics, but this kind of translation is already useful. I mean, one of the theorems I proved, it took me much more time to understand what they're saying than even to prove the theorem. I'm not exaggerating.
Right. Yeah.
See, what happens is, the problem with talking to mathematicians and physicists first, not only mathematicians, anybody else who asks a mathematical problem to you, who are not mathematicians, is to understand their question and put it in your own language to formulate even the question.
Right. Yeah,
So,
for that you yourself need to have a broader,
so it's, it's hard work.
Right.
And sometimes you say, I'm not interested, it's his problem and so on.
Would I be right in saying that your approach to mathematics is more of that of an artist than a scientist?
I don't know. No, I'm not an artist.
But it looks to me that you are driven by aesthetics a great deal.
That's absolutely correct. That's absolutely correct. I mean, okay, first, that's one statement. More important is, I think, for me, I want to understand some mathematics. I don't want to prove theorems as such. I mean, of course, I'm happy to prove theorems. But if something is there, it's not just, you can sometimes, prove something is a good theorem and so on, and you are satisfied. But I have to understand what is behind. As one of the mathematicians said, somewhat in fashion, said, you want to understand, you don't like numbers. So one example I can give is, Ramanan and I proved one theorem, one of the first paper in the algebraic computing. It was a very nice proof that some space is projective space. And it got published everywhere. But the proof was so complicated, we are not happy with that. That means we didn't understand what was happening there.
Right.
Then for more than a year, we worked and understood what was the real thing behind. And it's not only satisfactory, it is what gave ideas to much of our future work. Otherwise, that would have been just one theorem and then forgotten. So coming to your question, I don't know. I'm a mathematician, I think, neither artist nor scientist.
In some sense, the borderline between the intelligible and the beautiful is very hazy. It's not clear.
See, this is the French kind of thing, which other people make fun of. The necessity for clarity and understanding. Clarity. Things should not be, vague. You may have deep theorems and so on. If other people don't understand how to struggle, it's not.